Good morning all. In the previous class we have gone through the single phase AC system with a pure inductor. So whenever the pure inductor, if it is connected to the single phase AC system, what could be the behavior of the circuit? So that concept we have already studied. So in this class we are going to see if the pure capacitor, if it is connected across the AC supply system, then what could be the behavior of the circuit. So that concept we are going to deal in this class. So if you see the diagram of this pure capacitor, so let us consider the has the capacitor, pure capacitor, and to this pure capacitor I am supply a AC system, or AC system or AC supply system has been connected to this pure capacitor. So this is what the I am writing. So this is I and this is my capacitor C. And as we know that whenever if you want to see that capacitor always stores the energy in electrical field, so this capacitors always has the charges. So if you recall your background concept which you have studied in the +2, the charge and capacitor and the voltage concept, what is the relation between Q, C and V? We know the Q is equal to C into V. So this is what we have studied in our +2 studies. So if you write what is Q here, so I can write Q is equal to C. What is V here? V, I can take this one. So this is nothing but Vm sine omega t is come. So if you want to define what is the current, I, so you know the current definition of the current is nothing but the rate of change of charges or rate of change of flow of electrons. That is nothing but the mathematical it is given dq by dt. The rate of change of charges is nothing but a current. So this is the equation which is defined for the current. So if you take this equation, if you write instead of this q, substitute this value, so I will get here C Vm sine omega t. So this is what I am getting here. Again, if you simplify this equation here, so I am getting C Vm omega. So I am writing the derivative of sine omega t. So the derivative of sine omega t is nothing but so omega cos omega t. So this is the trigonometrical concept I am applying here. So again I can write this one is C Vm and this Vmax and W, this is by sine. I am converting the cos omega t into a sine, so that is nothing but omega t plus pi by 2. If you do this one, so you can convert cos omega t into sine omega t. Again further if you write this one again, so this is I can further simplify this one, I max by 1 by omega c and sine omega t plus pi by 2. So this is the equation I am writing here. So what is this? I can write again. So I is nothing but I can write it is Im sine omega t plus pi by 2. So this is my equation 2 and this is nothing but my equation 1. These two are the voltage and current in instantaneous equation. But here what is my Im here? What is my Im here? That is nothing but Vm by 1 by so Wc, or I can say here I can write Vm by Im is equal to 1 by Wc. I can write. So I can divide root 2 in each term here by root 2. If you do this one, what is Vm by root 2? What is Vm by root 2? That is nothing but the voltage. And what is Im by root 2? That is nothing but IRMS current. And this is also equal to 1 by omega c. So V by I is nothing but something like a resistance. So I can say it is a ohm property. So here 1 by omega c is nothing but it is called the Xc, where Xc is called the capacitive reactance, capacitive capacitive reactance. It is called capacitive reactance, measures in ohm, measures in ohm. So that is the concept we need to understand here. So Xc is a kind of reactance a kind of resistance property of the capacitor. So Xc. So further you can write X is equal to 1 by omega c, or you can write 1 by 2 by fc. So these are the different expressions we required so to understand or to do some numericals as well. Now if I take my instantaneous voltage and current, so this is instantaneous current and this is my instantaneous voltage we have. So these are the two equations, and from these two equations I can do the calculation for instantaneous power. Instantaneous power. So before going to do the instantaneous power calculation, I want to draw the waveform for I and V here, so that I can able to understand the which quantity is leading and which quantity is lagging by what angle. So that is I want to talk here. So if you take the voltage here, voltage is simply, it is nothing but the Vm sin omega t. It is simply Vm sin omega t. So it is no issue with this. You are getting it is 0. It is, you can say, pi by 2, 2 pi, pi, and this is 3 pi by 2 pi, something like this. So this is the axis is in negative direction, you can say. And here now if you want to draw the waveform for I current value, so here I am sin omega t plus pi by 2. It means that your current waveform is advanced with an angle of pi by 2, with the angle of pi by 2 with respect to the this voltage waveform. It is advanced to some angle here with the angle of pi by 2, with the angle of some pi by 2. So that is the meaning of this one. This is my volt current. So this is what we are getting, this voltage. Suppose if you want to calculate the instantaneous power that is V into I. So we know this, the product of these two, isn't it? The product of your voltage and current. I have to do this one, the product of this voltage and current. So if you see here at these points, if you identify these points, something like this. So from this point you can able to identify that. So from this point to this point, the product of voltage and current is both the quantities are the positive direction, a positive polarity. So this whatever the power we are getting, it is a positive polarity. And if you come to this second point here, so if here my this current, this voltage and current which are going, one is going in positive and one is in negative direction. So product of the plus and the minus, it is comes as a negative direction. Similarly, if you do here in this case, both the waveform and down are down direction or negative direction. So both the negative into negative, it is again coming in the positive direction. So likewise, you can write the you can product the power calculation. So this is the power calculation you can do here. So power calculations. So this is the product of one time it is getting, and this is what the instantaneous power calculation. If you observe this waveform, this power calculation, this whatever the instantaneous power is also double the frequency. Double the frequency you can say, or it is oscillating with twice the frequency of the fundamental, twice the frequency of the fundamental, or you can say. So if you want to calculate, the mathematical expression for this double the frequency waveform, then it could be, you can call it is Vm sin omega t Im sin omega t plus p by 2. So you just do the some simplification of this equation, then you are going to get this is what, and again I can write Vm by Im by 2, and this is sine into 2 omega t. So this is simply I'm doing some trigonometrical logics here, so this is what I'm getting. So by seeing this value, you can say our frequency of this instantaneous power is double the frequency. So this is what the mathematical expression, and this is what the pictorial diagram which is shown here. So in this case also, so in this case, even though my conductor pure capacitor is connected to, if the pure capacitor is connected to the AC system also, here for first quarter cycle it will takes the energy, and for another quarter cycle it will returns the energy. For first quarter cycle it will takes the energy, and for other quarter cycle it is returns the energy. Therefore the average power is become zero, because average power is become zero, because for first quarter cycle it takes the energy, capacitor takes the energy, and for second another quarter cycle capacitor supplies the energy or returns the energy, it returns the energy. So because of this reason, my average power, the final average power I want to calculate, that average power is become zero, whatever the average power. So we'll see the mathematically whether my average power is coming zero or not. So we'll go for that. So calculation of the P average, we'll see whether the 0 is coming or some other term is coming, that we're going to see here. So the P average power, if you want to calculate, so it is the 2 pi into 0 to 2 pi, and so P dWt, so you can say, and 1 by 2 pi again, 0 to 2 pi, whether my instantaneous power value you can take, this is Vm by 2 and sine 2 omega t into d omega t, this is what we are going to get. If you integrate this and apply the limits, so definitely you try this in your home, so you will going to get P average is equal to 0. So this is the mathematical proof of getting the average power is 0. But if you want to talk in general case, because for quarter cycle this this capacitor takes the energy, for another quarter cycle the capacitor returns the energy. Therefore the net power consumed by the capacitor is 0. The net power consumed by the capacitor is 0. That points also you can note here. You can note the first one is the average power is 0. This is the point. And what is the reason for average power is 0? For first quarter cycle it is going to take the energy, and for another quarter cycle it will returns the energy. So average of that power consumption by capacitor is 0. That is one point. The another point I want to talk here is that point. So that point I just want to talk here. So we'll do that one. After that again we'll come to that second point here. Okay, so we'll see the phasor representation, then we'll come for the second point here. The phasor representation we'll see. As we know that our the voltage as taking as a reference, so I'm taking this voltage as a reference, this voltage I'm taking as a reference, so I will show that phasor of this one is here. This is my voltage, the VRMS voltage I'm taking with the angle of 0 degrees is as a reference vector I'm taking. And what about the voltage, what about the current waveform? So current leading voltage by a 90 degrees. So this is what you can getting the information from this diagram. So you can represent the same thing in your vector diagram. So I can show the current leads voltage by 90 degrees. So this I can show in this direction. So this is what my current is leading by 90 degrees plus 90 degrees. So this is what the 90 degrees here, because my vectors is rotates in anti-clockwise direction. My vectors rotates in anti-clockwise direction. So whenever my vector is rotating anti-clockwise direction, so with respect to the reference vector, with respect to this reference vector, my current vector is leads by a 90 degrees, which leads by a 90 degrees. So that is the meaning. Otherwise my voltage lags current by a 90 degrees. So this is what the context we need to understand by taking the vector diagram for your electrical this AC system if it is connected to a pure capacitor. So now the second point we observed is here the second point we observed is your current leads voltage by 90 degrees, otherwise the voltage lags current by 90 degrees. So this is what the 2 points conclusions we are getting from this kind of observation what we can talk. So one more point we need to note here, that is the third point you can take here. So generally capacitor stores the energy in the form of electric field, So the stored energy of the capacitor is nothing but this half CV square. So half CV square is stored energy. Suppose you want to calculate the what is the maximum energy stored by the capacitor, then half CV max square. So this is the maximum energy stored. These are the joules you can say. So these are the some 3 points you need to remember to understand this concept. So to further clarify a very clear manner, so I will take one numerical and I will do this numerical so that some of the doubts you maybe have that can be clarified here. So a 318 microfarad the capacitor is connected to 200 volts 50 hertz supply. Then determine the first is capacitive reactance. The second point is maximum current. The third point they are asking is RMS value of current. And another point they are asking is the maximum instantaneous charge. So maximum instantaneous charge. The last question they are asking is the maximum energy stored by the capacitor. So these are the question they are asking to calculate. So we'll see this one, then you can easily do this one. Okay, so capacitor is given, it is 318 microfarad. Fine, I can convert this into 318 into 10 to the power of minus 6 farad, and this VRMS or voltage is given 200 volts. The frequency is given 50 hertz. So these are the things has been given to us. So the first point they are asking to find what is the XC inductive. So what is that formula we know? So this is what the formula we have, 2 pi FC. Substitute these values, so you will get the thing what you need here. So you can take this is 10 ohms. The second point they are asking is to find the maximum current. Maximum current is nothing but I can write V max by XC. So this is nothing but how will you get the V max? Root 2 into VRMS. What is the VRMS voltage here? That is 200 by this XC. What is the XC? 10. If you do this one, you will get 28.28 amperes. Similarly, go for the third point here. They are asking to find IRMS current. So IRMS current is nothing but I can write here V by XC I can take. So 200 by 10 you can do, then also you'll get 20 amperes. Otherwise I is nothing but IRM is nothing but IM by root 2. If you do this one also, you will get the 20 amperes. So this is also another kind of answer you can get, another expression. And the another point is we have to ask to calculate the maximum charge. So you know what is the charge relation, the Q is equal to C into V, something like that. If you want to calculate what is the maximum charge, so this is nothing but V into the V max. This is what. So capacitor, you know, 318 into 10 to the power of minus 6, and what is V max? V max is nothing but root 2 into this RMS value of the voltage. Do this, you will get 0.09 coulombs. This is how you will get. And the third point is asking to calculate the maximum energy. So as we know, half CV max square. If you do this, then you will get this value from here, root 2 into 200. So this value you are getting 12.72 joules. So these are the answers we are getting for all the questions they are asked for to determine the different values, so capacitive reactance, inductive reactance, and this maximum energy stored. And I hope, I think with this theoretical part as well as for this numerical, I think you have understood this concept, and will conclude this session for today.